Okay, we're recording. All right, we barely started example 6.3, right?
Right.
And so I just glanced at this and I noticed that I still had, the only thing I really did is I put this in red so that when I change this, I like to have the problem I'm working on in my spreadsheet because sometimes I will use it in my legend in my graphs. And I'll even remember to do that. So like this data right here, I can just come in here and just click before that comma, put 6.3, and then 6.3 if I give myself where is my quick sharp styles? Quick layout, here we go. So then you see I can have example 6.3 in my dialog box. Okay. So this is a drawdown, high rate. We're going to examine it using pseudo pressure. Remember that apparent pressure is just pseudo pressure times some constant. So it's in the thousands rather than in the millions. I don't have a problem with using pseudo pressure, and it's an extra step to do apparent pressure. And apparent pressures, to me, are misleading. Because it's not 5,000 if it's 4,000 pounds or something like that. So all the problems that we do from here on out, I'm going to use pseudo pressure. And you'll see in your tables there's always an option for your equations that you use to use pseudo pressure. We'll go over that carefully. So I think the example asks us, and they give us information. And we're also getting used to the idea that we're going to just use our last problem as a template for our next problem. So that's how I started this. There's some stuff on this page that I'll go through again because I can't remember what I've changed and what I haven't changed. Okay. We got the rate in there. We got 10% porosity in there. We got 200 degrees didn't change. I think all the problems in this textbook are 200 degrees. Now, total system compressibility, this is textbook input, is 112 times 10 to the 6th, and there it is, 1.12 times 10 to the 4th. Initial pressure is average pressure. Now, this becomes important because when I have to do fluid properties, I try to do it at average reservoir pressure. Now, most of the situations that we're going to be doing in this textbook assume this is a new reservoir, okay? And we're hardly ever really looking at situations where it's a subsequent year after year pressure buildups, where we would want to know what the average reservoir pressure is so that we can calculate the fluid properties at a different average reservoir pressure. So you'll see this type of I know the recording doesn't pick up where my mouse is, but you guys can see where my mouse is.
Yeah, it does.
Pardon?
The video does. It does pick it up.
It picks up my mouse?
Mm-hmm. Yeah.
Okay. So PI equals P bar. So what they're telling us, this is a new reservoir. Okay? That's the importance of that statement. And H is 40. I think I have that in there. And I got a water saturation of 25, but I converted that to a gas saturation of 75. And remember the Z, I remember now, we didn't use it all, it has the wrong units, and we calculated a totally different Z, so we're ignoring that. Okay, I am going to scoop this information over, and then scoop this information out, and zoom back in. And did it give us a rate of gravity?
Yeah, it's on.
Oh yeah, 0.85. And then here's their V sub G that we put in reservoir cubic feet per standard cubic feet, and we calculate our V sub G using our Visual Basic. and we see that we have 4% air, okay? Just to let us know that if we're going to use our PVT package, always. We're not, unless we don't know something or other, but the idea is that we recognize we're going to have a subtle error in their fluid properties and our fluid properties. We don't have exactly the same B sub G as they do. All right, it doesn't look like I've changed this number, P average. 305, 4290 must be left over from the last problem, is that right? Okay, I'm going to change 4290 to 3056.
Wait, that's the adjusted.
Oh, okay, thank you. So, here we have 4290s left, thank you. We're not going to use that adjusted pressure for anything. RW is 0.3, we have that. That's a third of a foot is the radius of our well. Adjusted pressure for 1 hour, we're not going to use that, and you'd never be given that. We have to get that from our graphical analysis. Gas viscosity is 0.0254. I box up here usually what they give us, and then I haven't calculated a gas viscosity. Just would have had to look at check the air. Remember, preserve keystrokes. I use the same thing, just change the spelling. UG gives me the gas viscosity. And I can check the relative error on that. Equals what they got minus what I get, divided by what they got. And it's a 19% error. Okay. No big deal. Okay, so I'm done with this data input. Let's move it out of the way. And it looks like either this chart is left over or I created it last week. Which was it? It's just the data.
You made it last week.
Yeah, you made it last week.
I made it last week. Okay, so it's a quick look at the data and the derivative. And let's see. I think I'm going to try to standardize how I do derivatives. I did average time and I did the log derivative there. But I'm going to do the log derivative, so I skip. So I'll have 2 less than my data. And then this smooths it, and I'll plot it. I no longer need the average time. I'll now be plotting it versus not really the closer to midpoint time. I get a little bit smoother plot when I do that. And although that looks a little noisy, it's fairly flat, and you can see from our data, it looks like we got a pretty good straight line when we plot the semi-log of. This is a drawdown, so this is just time. Well test units are hours. And over here we have pseudo pressure. I'm not going to put down the units, but it's PSI squared percent of voice. And over here we have our derivative. Oh, we got more people than I thought.
How do you get the number gas compressibility?
How did I get compressibility? Here's the one I gave you. The one I got, I used the VB function, CG.
In the previous sheet, we are using the PE rate, but now we are using PI.
Okay, I want to go over a couple things here. This is my gas compressibility. This next cell is CT. Let me zoom in just a little bit here. this next cell is CT, which is that gas compressibility I calculated times the gas saturation. That's what I use in this course for the approximation. And then I compared my CT with their CT, and I got an 11% difference. So basically, from a volumetric standpoint, 4% air, I know this textbook uses a different gas viscosity than I do, so I'm always going to get a pretty good size air with viscosity and my CT. So when I don't get exactly the same numbers as a result, I know a little bit why. But I want you to get used to something that you can always pull up. You're never going to be given a real world problem where someone's going to tell you what the apparent pressure at piece of 1 hour is and go with that. You're going to have to calculate all these things. Okay, so I'm going to kind of rush to judgment here, but I'm assuming all these points are a straight line. And this is logarithmic straight line, right? Okay. Let's get rid of our. There we go. Now let's look there. Okay, so our regression coefficient for all of the data is 0.9989. So I don't think there's anything other than radial flow on this. So when I calculate a slope, and this is probably left over, okay, I got rid of this, the slope of this data, let's see what this is the y, see, they're all off, is the y's versus the log of the x's. There's my slope. And all of the equations that we have in the tables of the textbooks, you'd think that they flip the signs for drawdowns and buildups, because obviously the pressure goes in one direction on a buildup and goes the other direction on a drawdown. But it's always the absolute value. So if I want to make this a template so it works for buildups and drawdowns, I would just say ABS. Because it's all of my equations are expecting a positive slope. My y is negative, or my intercept negative. And let's see it. Here's your intercept on my graph is 8 times 10 to the 8. And that's point, so that's my number here. And this 7 times 10 to the 6 times the log of x, the slope is I know what I need to do. I need to open the textbook here. Any numbers in here, but I can do that later. Okay, I think we're ready to calculate permanent skin. Yeah.
Can you give me the quote that you slope and intercept?
Yep, speak up.
How do you come with the slope and intercept?
I used all the data. Pseudo pressure versus time. But you can see built into my, I have right where my cursor is blinking, it says log. So I'm taking the log base 10 of those numbers. And one of the reasons I have a different intercept, this is the log of an intercept, and down, well, it's the same. Yeah, the intercept would be the same manually. Okay, it is actually giving me the intercept. Anyway, we'll move on. I'm not, I can see up here in my formula bar that this 162.6 is that leftover oil equation that I used on that previous equation. I'm gonna open my textbook and start copying over the equations that we're gonna use for pseudo pressure. What page are we on? 120?
Probably about 130.
Okay, so we're doing a drawdown. Okay, so this table 6.1 gets continued on other pages. This isn't all of 6.1 that we're looking at. Here's oil. These were all, remember, the industry made oil started as an oil business, then later on became a natural gas business. So all the equations were converted from oil to gas. So here's the oil, and then you can see this 162.6 coefficient remains the same as if we're using gas. But we have to use gas formation volume factor. And it's in that reservoir barrels per MCF, and that's because our rate's now in MCF a day, and over here it's in stock tank barrels per day. So we gotta move on down to 6.1 continue. And then we can use pressure and time, using pressure squared and time. We're still not there. But we're getting closer. I can see this 1637 is the coefficient that I'm looking for. So it can be pretty confusing. Finally, part 3, table 6.1, we have the equation I'm looking for. Pseudo pressure and time. And it's actually a much simpler equation to use because we lost the V sub G and the mu sub G, and the change in Z and viscosity are built into the fact that we're plotting pseudo pressure, which incorporates the changes in viscosity and Z factor as we go. So we only got reservoir temperature, that capital T means it's going to be in degrees Rankine. We have a slope and an H. This becomes pretty easy. So I'm going to change, well, I don't know whether to change everything up here. I'll do that some different ways. Okay, so the 162.6, I'm going to change to 1637. N4 is B sub G. We no longer have a B sub G, but instead we have temperature. 460 plus 200. And N6 was viscosity. We no longer have viscosity, but we have rate. The reason we didn't have rate before is we had a form of the equation that we were doing a variable rate. We were plotting delta P over Q and looking for the change in that. So we actually have to put in a Q on this one. So now I've got my Q, my temperature, and my coefficient. Let's look at the denominator. It was calculating the Lee slope, but I want to calculate my slope. And it's got H in there. So I get a term of 63.41. And this is example 6.3. Where are we here? I'm going to go further. Isn't that the 6.3?
150 feet.
Huh?
150 feet.
Oh, here we are. Oh, I won't even be able to compare their slopes, but I can compare the results. They have 57 millimeters. Okay, I've got this backwards. I'm going to highlight this yellow, and I'm going to take off this highlighting here, and thought I was gonna take off this highlight. And they got 57. I got a slightly different number. Not too much there. 63 versus 57. Any questions? So in transient pressure analysis for radial flow, that's what we fundamentally do. If we got a drawdown or a buildup, we expect our data to change with the logarithm of time. And that change should give us a semi-log straight line whose slope is inversely proportional to permeability. A key factor in all of reservoir engineering is knowing what the permeability is. Fundamental property of a reservoir. Is the permeability 63 millidarcies everywhere in the reservoir? No, just some kind of average. It's an effective permeability or a system permeability.
Like, can we say that is the reason why the value is different from that of the textbook?
Oh, you want me to discuss that?
As you said, it's not that, it's more or less like the average reliability in the reservoir. So
Oh.
can we just state that because of their kind of difference slightly, the variability is kind of,
The difference between my 63 and their 57 has to do with these three errors right here.
okay.
Which errors?
The error in the formation volume factor, the error, a big error there is in viscosity. See, these tend to get in total system compressibility. They have a different viscosity function throughout this book. And viscosity is used to calculate pseudopressure. So my pseudopressure and their pseudopressure that they get PAs from are going to be slightly different. So they tend to wash out a little bit, but based on the gas gravity and what I think is a better, let's say that my number is the right number. I'm getting about a 10% error. See, it's very close. I'm beating the 19% viscosity error. It's not, in other words, something in there between the Z factor and this cancel, because pseudopressure is the integration overpressure of Z and mu. So when we're doing these problems, we're really just using the textbook as to make sure that we're within the ballpark. But I can certainly accept the fact that I got a 10% difference in my answer in the textbook, knowing I had these differences going in. Is everybody good with that?
So when you calculate like the radius of investigation and the investigated gas in place, are you going to use your calculated values?
Yeah.
Okay.
I actually, I'm not going to use, I don't even know if that, I think this is from the last problem. I'm not going to use any PAs. I don't use their V sub G. I don't use their mu sub G, and I'm not going to use their total system compressibility. Okay? I am going to use my values when I calculate anything.
Okay.
Because, well, I'm certainly not going to go mixed mode. You see, I'm using my properties to calculate pseudopressure. And so then I'm not going to come back and use their viscosity or their compressibility when I calculate the skin. I would definitely be using different correlations to calculate different parts of the problem. Okay, let's look at our textbook and come up with a skinny quotient.
Dr. Calvin,
Yes.
when they do the permeability, why do they calculate this? They're using the same equation, but they also have TSC and PSC in there in the book. When they do
Which equation are you looking at?
Well, I'm looking at the equation where they show the actual calculation.
Are they doing it in pseudo pressure? Using pseudo pressure? They're not doing pseudo pressure. They're using apparent pressures.
Well, they have for the standard conditions in there.
Yeah.
I was just wondering why they did that.
You'll have to show me what page.
If you go down, it's page 124, which I guess is probably the next page.
Okay.
Yeah, right there.
This is,
Maybe I'm jumping ahead.
eh,
I don't know.
well, you'd have to tell me what you get, like when you multiply 138 times TSC divided by TSC.
Oh, and they're using, I guess it's a whole different equation. I just
Yeah.
didn't understand why they
Yeah.
were doing that.
But incidentally, they got 57 using the liquid solution, and I guess they use another solution to get 55. Anyway, we're trying to get to our table. Where's our table again? 6.1 continued. The third time.
Yeah.
Here we go. So here's our skin equation. And I can tell you right now, we're going to need this pseudo pressure at 1 hour. And this is an important concept. Most of this is actually the same. The skin equations don't change that much. Okay, I need this pseudo pressure at 1 hour. And let's look at our graph. My time units are 1 hour. And the log of 1 is 0. So basically, my intercept is P sub 1 hour. See how that works out? Now,
Please can you come with that?
pardon?
I mean, can you come with that again? You say your intercept is the P of
Okay,
L.
let's look at our graph. This is a four-man axis I'm in my minor tick marks. Let me figure out how to do it. Bound units. Text options. Axis options.
Did you say you're trying to do tick mark?
I just want to add my minor tick marks.
Go all the way down, you see where it says tick mark?
Oh, yeah. Okay. Then I can kind of see that I got a logarithmic scale. 0.1, 1 hour. So I have some data below an hour and above an hour. Now, because my data is at 1 hour, I actually have a data point at 1 hour. See that? It's my pseudo pressure at 1 hour is 803,469,209. My intercept is almost the same number because there's just a little bit of movement around there. Do I use the actual data at 1 hour or the best fit data at 1 hour? Pardon? Unfortunately, we're wrong there. Because in some cases, we may not be in the middle time region. In which case, testing. This is our middle time region. In this case, we happen to capture 1 hour in our middle time region, but we're really looking for a data point as if it were on the straight line. And so if this is 1 hour, we would never want to use a data point that was different. We want to use a data point that's on the straight line. You have to remember this. We ignore completely what our actual pressure and pseudo pressure are at 1 hour. It wants the pressure on the middle time region straight line at 1 hour. Okay? Because then it's gonna subtract an actual PWF. And that difference is gonna tell us how much skin we have. Now, let's see how well we're set up here. I got 1.151. Now, I'm looking for a ratio, but I had the wrong ratio, K16. Now, I'm gonna take this first term, and I'm gonna get the pseudopressure initial, which incidentally I don't think I have anywhere. Hold on. And I think we're all right because this is a drawdown. Pseudopressure minus pseudopressure at 1 hour. I think we're okay. But I'm still curious. I'm jumping ahead. Oh yeah, here's what I was looking for. It's right here in front of me. If we're doing a build-up test, this is a little bit different. It's piece of 1 hour minus PWF. Our next test is going to be a build-up test. If we're doing a drawdown, it's the average reservoir pseudopressure minus pseudopressure 1 hour. Regardless, the pseudopressure 1 hour always appears in this equation over M. But it depends upon whether we're doing a flow test, which I'll refer to as a drawdown, or a build-up. Okay, all the other terms in this equation are the same. So we're going to be careful when we use this as a template and go to the next one if we're changing from a build-up to a drawdown. Okay, we're okay. Except for I've never calculated the pseudopressure, but I'm not going to use this number that they gave us. Let's just change this to pseudopressure. I. Copy one of these things that has everything in it and change the spelling to M of P. And now I've got initial pseudopressure. Okay? And handy that shading got copied because everything else in that bolded box is textbook given, but I've added up there with the initial pseudopressure. So the textbook would have used that that apparent initial pressure in this equation. But I've got to use delta, which is this minus the intercept. Because the intercept is at 1 hour, okay? When we're doing a build-up, this is not going to be as easy. But our drawdown at 1 hour is the intercept. Okay, so I got my numerator, and now for my denominator, I need to divide by the slope. And I don't know what this K17 is left in my equation. Oh, that's I think everything else may be good. N13 is my K, J11 is my porosity, viscosity, and I'm going to use my viscosity, and my total system compressibility. RW squared is over here, 0.3, and then we add our constant 3.23. 79. And what did the textbook get for this problem? I'm down, aren't I? Is this it? That's 6.2. We're 6.3. Here's 6.3 starting. 8.3. -5% difference than the textbook. So when you're working through these examples, you can expect this amount of error. You're not going to match the textbook exactly. So we actually did the previous problem. I can't tell which one I'm on here. Okay, here's where we are. When we did 6.2, we did two ways. We did the constant pressure example, and then we did it with superposition. And we actually honored their technique of using apparent pressures, which is just a constant multiplication of pseudo pressures. The slopes are going to have to be exactly the same. Okay. Always, no matter what the textbook asks us to do, we want to examine these data sets as fully as possible. So we have a radius of investigation, and I think that should be around here somewhere. We're done with skin, we're done with this data. This is from the last problem, I don't need that at all anymore. That's from the last problem, I don't need that anymore. I don't know what this is. Don't I have an equation for the radius of investigation?
.12.
Okay. What page? I passed it. Okay, and we're going to have two. This is our drawdown. And it's really the same equations. The denominator is 948 phi mu c sub t. It's just that on a buildup, we usually refer to delta t as time, as shut-in time. So really, there's just one equation. So that you can see why perm is such an important reservoir parameter, because it immediately tells me how much reservoir I look at a certain amount of time. Perm times all of our data was still radial flow, so we used the last point. Now, in a situation I've got this drawn as a buildup rather than a drawdown. In a situation where our data deviates from the straight line, we wouldn't use the last test point time. We would use the last time that we're still in the middle time region. Because at that point in time, we saw a boundary. So the radius we investigated ends when we see a boundary. If we're still in the middle time region, which in this example, there's no reservoir storage data, there's no boundary down data, 100% of the data points middle time region. So we'll use the last time. 3 hours. See, I'm highlighted over there. Okay. My equation.
How do we know that all this data was in the middle time region if there was no?
You know, that's an excellent question. And basically, I kind of rushed to judgment. I plotted it up there, and it was a semi-log straight line on all the data. But we'll check it. I haven't forgotten, what you're asking is a very important point, so we'll check it.
Sounds good.
See, if we know the perm, we can actually estimate when we should start to see. And we can put this on a type curve and some other things. But we'll have to do this. In this particular case, I just saw that all my data was a semi-log straight line. That could be misleading, but the regression coefficient was 0.996. So after looking at a lot of these, I would guess that it's all middle time region data. And no boundary dominated data, no wellbore storage distortion data. But it was kind of a rush to jump. Okay, divided by, I'm going to need an open plan. Another open plan. 948 times 5 UC sub t, 5 times my mu times my c sub t. Close my denominator and then raise everything to the 0.5. So 814 feet. Actually, and I like to look at gas in place. This is my own nomenclature here. How much gas have I looked at? Well, we got an equation. We usually use 43650 and convert to area, but I've already got radius, so I'm going to use pi r squared. So there's my area. SGPH. Divided by my formation volume factor, reservoir cubic feet per standard cubic. And that's in standard cubic feet. I'm going to at least divide it by 1,000 and get MCF. And if I take that number and then divide it by 1,000,000, I have it in BCF. Okay? So that's how much gas I've looked at. I've already looked at a commercial reservoir in 3 hours. Yes?
Could you click on the radius of investigation again real quick?
KT times permeability is basically, everything else is kind of constant. If you increase your perm, you can see more in the same amount of time. You increase your time, you get to see more. The numerator's the concept that you need to keep there. And I did this in my office so I can check if I got the same numbers over here. I got 840 to 814 for some strange reason. But I might have used some of these numbers. Okay, your apparent wellbore radius is, who can comment on this skin? Who's got worked with skins before?
Don't like it?
Yes. How much? It needs simulation. Is skin at 8 bad or real bad?
It's real bad.
It's real bad. Okay. On natural completions, you kind of expect a skin of 1. That'd be maybe some mud filtration. Okay. A skin of 8 is terrible. It's huge. Now, these examples were synthetically developed or something like that, so I don't know a lot about the well. But if I had a skin of A, I would start investigating other things. There's other kinds of damage rather than the PowerPoint slide I showed of idealized mud infiltration damage. One is partial penetration. You could drill into the top of a reservoir, but not fully penetrate the reservoir, okay? And your flow wouldn't really be radial at first because it would actually be semi-hemispherically, okay? So you would get a lot more flow, your rate would be high. But when the rate's dominated by the radial flow in, but you see, you're not fully penetrating into the reservoir, so you could have a partial penetration contribution to skin other than just damage. Because basically, if I saw a skin of 8, I'd look for other problems. Okay, because it's really hard to get a skin of 8 just from mud infiltration. But the comments are well taken. This well would need to be stimulated. There's other things you can do, like you can calculate the flow efficiency based on the skin, and you can calculate a hypothetical rate. And one of the ideas of this problem is to look at the rate, look at the perm, and continue on using 100 correlations and see how much of this was non-Darcy flow. I would never, knowing what I know about how these correlations were developed, I would never use them. They're not substantiated by enough data. Okay, but it is another thing to look at. You could have a skin contribution based on non-Darcy flow. But look at what the textbook did to get this. We're after this. 6.3. 6.3. So after getting a perm of 57 and a large skin, let's just look at the steps they did. They estimated a turbulence factor based on the perm and the porosity. They don't tell you how tight a correlation this is, okay? And they don't tell you over what range of rocks this was given for. And they don't tell you whether this range of rocks was dominated by limestone, dolomite, or sandstone. So you really have to question about this turbulence factor, okay? Then once they get the turbulence factor, they've just started. Then they get the group, B sub QD, which is a function of the turbulence factor, the perm, not much else new there. And then they get another term, the term B. This is a lot of work, guys. And then I think they finally have to use a graph. They're not done yet. They still haven't got anything. I'm going down the left column. They're still working on this. And I'm going down the right column. You see, this is like 4 pages. And then they finally get a non-Darcy flow coefficient. I'm on like the 6th column of this thing here. So they get non-Darcy flow coefficient of 2.5. And so if they say their skin is equal to some contribution of what we're getting from our buildup, a number about 8.3, then they say the non-Darcy flow is 2.5, so the only damage that really the formation has is 5.8. Okay, I would never have you do all those equations, but it's good to kind of look at what could be done if you had a large skin factor. Did the non-Darcy flow coefficient actually explain the large skin? No. You still got a huge skin. 5.8 is huge, okay? So I'm glad the textbook worked this out, but I would never have you do that because I don't have confidence in this final result. You saw how many convolutions they had to go through and how many correlations, and it's not based on that great a data. Okay, so I think we'll go back to our spreadsheet.
Can we just imply that if we have a sin number of 8 or x, y, z in other cases, so the major part of the skin is actually the mechanical skin, not the pseudo skin.
Right. That procedure broke the skin into two components, non-Darcy flow and mechanical damage, if you want to call it that. But again, in mechanical damage still could have other components. You can find in Economides' textbook a skin equation that has 8 parts. Okay? You can also, now, it wouldn't be the case, and it could be having to do with not enough perforations in the pipe. You can have perforation skin. So there's other things that could contribute. But anytime you're doing a well test analysis and you get a large skin, maybe instead of a stimulation, maybe you need to add perps. You know, but there's techniques in Economies is our standard textbook we use in our undergraduate education for production engineering. But they have a great section on how to calculate skins from design, from a design standpoint, and try to remove that skin as good as you can from a mechanical design standpoint. We're just looking at this problem right here. We don't know how it was designed, but this is what we did. I'm just trying to emphasize the point. When skin is 8, let's look for what the problem is. And back to your question about how do we know that this is the middle time region? I may have some doubt at this time if I get a huge skin, that I'm actually picking the right line. Okay, parent wellbore radius equals RWE to the minus S. I let that one memorize. So instead of the reservoir thinking it's seeing a 0.3 radius, 0.3 feet radius, it's actually behaving like it's seeing a radius very, very small. Okay. We might be ready. Let's see if I do this mic over here. I did a lot of work over here. We got a lot of time. I think what we're going to go ahead and do is, we've got 2 hours left. I want to do one other problem, but I want to kind of introduce us to type curves. So here's a skin storage type curve. And let's just talk about this. This is our data. I may or may not have us do this. I may come back to this problem and have us finish it up. It's not of great interest. But what I've done here is I can calculate T sub D over that, and I can calculate everything here once I know perm and skin. And I can plot this data on, yes?
When you say our data, are you saying for this problem?
Yes.
Okay.
This is this problem.
Okay.
It says down here, this is what I did in my office, this is what we're doing in class, and I've already worked,
Okay.
I had in my office.
Okay.
So we can carry this on. This type curve can be extremely helpful when we have data that's influenced by wellbore storage or skim. Now, our data, I got a highlight. I want to, okay. Here's our derivative data. you see, remember, on a semi-log straight line, the derivative is flat. So, although there's a little bit of noise to it, this is kind of my best fit. And these families of curves are for C sub D e to the 2s values. And when we're doing type curve matching, we can get a third parameter. One of the third parameter that we don't have, since we don't have any wellbore storage distorted data, we could actually calculate the size of our wellbore from this. This data, this type curve is a much bigger advantage when we have lower perm or earlier time and our data is back in this region. We can actually get a simultaneous fit. The separation between the red points and the purple points are fixed. So we can simultaneously fit the data and the derivative data, especially when they're both curves, and without even seeing the middle time region. Calculate a perm, calculate a skin, and calculate a wellbore storage.
So what's the degree of reliability in that case?
What's that?
The degree of reliability in that case, because we haven't seen MPR yet, and we are going to find the permeability and the other result parameters by using the type curve.
If you're simultaneously fitting both the data and the derivative data, and you see you're fitting one to solid lines and one to dashed lines there, your confidence is good.
But usually the every time region is very messed up.
Pardon?
What I see like from tests that I looked at, usually every time region is messed up. And you have to get really high resolution gauge to get the every time region. Especially if you have high permeability.
If you have high permeability, you're off to the right away. So but then you usually have middle time region. The problems, some of the problems in well test analysis is if you have high perm and you hit a boundary right away, you may never have middle time region. Okay.
Yeah, and now with the horizontal well, it makes it.
Well, okay, let's just back up. We're doing radial flow and then we're going to do linear flow. When we're looking at horizontal wells, we're looking at horizontal wells that have multi-stage fracs. It's all linear flow. We don't use this type curve to analyze anything other than probably Gulf Coast wells or worldwide wells where no stimulation is required to produce them in commercial rates. We still have those kind of wells, but for people that are going to be working lower 48 continental United States, we'll never look at radial flow. But it's valid from a historical standpoint. It's still valid for high perm reservoirs that do not require stimulation or horizontal wells. And a lot of those wells are still being produced, and so to analyze them, we still use radial flow. But there's a good development from the radial flow to the linear. And incidentally, I must why everybody here. It may work out, the next test is an overhaul of Chapter 6. It may be I just have it over radial flow. And then the next test picks up linear flow. I don't know how things are going to work out, but just see how much I can finish between tonight and next week, because the week after that we have a test, if I remember right. Okay. I don't think we're going to go to the trouble in class tonight to do this for this problem, but we may catch up on it eventually, because it's not of that great of an interest. It's more interesting when we have more than the middle time region. It should be obvious at this point in time that our data is fairly substantially obvious middle time region data. Because I'm able to make this plot, I'm actually able to change time and pressures into dimensionless time and into dimensionless pressure, knowing perm and skin, and placing my data on this plot. Actually, knowing perm fixes my y-axis. I still don't know level or storage, so my x-axis is still variable. I just did the best job. I can move that a little bit to the right or left because my lines are horizontal. I can't move it too far to the left because I move out of the middle time region. Okay, but this is the kind of plot that helps me substantiate when I get done that I did in fact make the correct analysis. But it also is an opportunity to look at a type curve from the standpoint that we can do an analysis even if our data is where I've got that big huge circle prior to the middle time region. Questions? You know, when I work out on this in the office, I begin to carry things. I got that from my type curve after the plot. So basically, I calculated some coefficients. What did I get C sub D? Okay, I have to. Hold on. Okay, so having done this, I'll briefly go through what I went through in this procedure. I can calculate a coefficient right here that converts my delta pseudopressure to dimensionless pressure. And that coefficient is only a function of things that I already know. Reservoir temperature, height, flow rate, permeability. Okay? So that's my height adjuster. It takes all my data and my derivative data and puts it fixes it. Okay, so that when I'm on my type curve, I only have one handle left. I can slide that to the right and to the left. Okay? I can't slide the red or purple data too far to the left because I'll move out of the middle time region. I can take it pretty far to the right. At that point in time, I can estimate my C sub D e to the 2s. Okay? At that point in time, I can estimate C sub D e to the 2s. Even if I shift it way to the right or way to the left, I'm still in a pretty tight band there, up and down this scale here, of C sub D e to the 2s.
Excuse me.
Yeah.
For the type curve, the separation between the derivative and the pressure plot, is it only
It's fixed.
affected by the
That one coefficient fixes both. Okay? Both my y prime, see, I'm using the same coefficient. I've got my derivative, which is a delta pseudopressure derivative, which we've done, okay? But both my y and my y prime use the same coefficient. Basically a function of perm. So that separation between the red and whatever color I had up there, purple, that's fixed. I don't have a separate coefficient for my y prime data and my y data.
You mean fixed for the time, right?
No, fixed for the separation in the y direction.
I know, but how do you get the fixed value? Is it only
Okay,
affected by
here
the
is the procedure that I went through to fix my x-axis, okay? I estimated. You see, if I take this to the left, I can get a little bit above that. If I take it to the right, I get a little bit below that, okay? But there's a pretty tight range of c to d, e to the two s's, okay? Now, I know s, I don't know c to d. I gotta have c to d to get my time coefficient. I got everything else, I got perm and I got RWA. So I picked a c sub d, e the 2s. After moving it to the right and left as much as I can, you can see it's just a round number, okay? But from that, I can get a c sub d because I know what e to the 2s is. I've got a skin. So I can get a c sub d. And then I can get an x coefficient that's a function of that c sub d, okay? Everything else I know, frosty, RW.
What is C sub D? Is the dimensionless liquid storage coefficient?
Yes. You can see I've been a little bit slow here because in learning this in the office, I used their mu g instead of, I didn't even calculate my mu g. I was working as fast as I could. But you can see that my x multiplier, I had to add one other thing. I had to know something about wellbore storage. But I had an estimator, just based on this elevation. See, by fixing my middle time region derivative along the 0.5 line, it automatically basically set, because there wasn't a lot of wow to it, where my C sub D E to the 2S is. So I can make a separate pass, I can refine that, but that C sub D E to the 2S scale's got changes rapidly in magnitude up and down there. So that's how I got my best fit.
And
I don't recommend this procedure for this type of well. This type curve is really for when you have both wellbore storage and middle time region data. Okay? That's the primary use of this type curve. And it's extremely helpful when you don't have middle time region data and only have wellbore storage data. You can still get a type curve match, come up with perm and skin.
so the type curve that we're using here is the same concept as the modeling that we use in the software, or it's a different.
We're looking at analytic solution based on dimensionless variables. And we can put our real-time data over those things just using some arbitrary X and Y match. And then from that X, from the Y match, we can get perm. From the X match, we can get some combination of skin and wellbore storage. If you're doing a type curve match without middle time region, you cannot break out skin and wellbore storage. You're always going to end up with a C sub D E to the 2S. Only if you have middle time region, you can get that intercept point. Can you get skin and then separate wellbore storage from skin? We'll use this type curve some more. And what we'll do is we'll take a break, and before we start on the next problem, and on content, I've given you this and all the other type curves we're going to use in chapter 6. And I've given you, in that same spreadsheet, some more software for pseudotime, which we'll use in the next example problem. So let's take 8 to 10 minutes and pause the lecture, and you can download that spreadsheet and start the next problem. Okay, how many of you have 2 workbooks open? One that we've been working on, and another one that's doesn't have this on it, that you downloaded from B2L. Does everybody have 2 notebooks open? Okay. Now, there's probably at least 100 ways to do what I'm going to do next, but here's what I consider the easiest, okay? Let's take example 6.4 and do a move or copy, create a copy, and put it in the workbook that we've been putting it in at the end. That's step 1.
I mean, can you come with that again?
Huh?
I mean, can you come with that again? You move the sheet to the other one.
Oh, how did I do that?
Yeah.
Okay, there's other stuff here we'll look at here in a second, but I just want to look at example 6.4 data. I've added this. I just added this during the break. This is what I set you up here. So I want to put this worksheet in my other workbook.
Okay. Good. Okay.
So I right-click the tab and hit move or copy. I create a copy, and then on this top dialog box, it gives me the listing of both the spreadsheets. I go to the spreadsheet I'm working on and I put it someplace. Okay?
Yep.
Now we're half done. What else do I gotta do? I gave you some software. Okay, so the module I gave you is, well, we don't need ARPS right now, but we might as well grab it now. And pseudotime is the one I needed. So hopefully you have your first spreadsheet here and your second spreadsheet here. To move pseudotime up here, all I have to do is move it up there, and then pseudotime appears in both spreadsheets. And you might as well, while you're at it, go ahead and take the ARPS module up there. Now I can close this spreadsheet, and I'll have pseudotime and ARPS in my other spreadsheet.
Where are we moving pseudotime?
Okay.
I'm sorry, you're talking move that.
You have,
I'm at that spot.
if you in Alt F11 in your VB, you have both your workbooks.
The last.
Okay? They're both open. So this is the one I had open first. And I have this gas PVT that we've been working on.
So we're just moving the macros along with the,
Yeah.
oh, okay.
So also I can drop and drag. VB, if I had 2 workbooks open, I can just drop and drag VB from one notebook to another.
Okay.
Okay, so I'm done in VB, and I'm done with this notebook. And now I'm in the workbook that I have been working on, except for I had my 6.4 data. And if I go to VB, I also have this new pseudotime functions that I'm going to be using for build up and for drawdown. Okay?
So you want us to move the VB to the old workbook? Okay.
You don't actually move it, you copy it. When you drop and drag, you leave where it used to be, and you also put it where your destination is.
Okay. Put in a copy extra.
but yeah, there's several hundred ways to do those operations, as you know in Excel. Okay, so up until now, we looked at only at drawdowns. Example 1 and 2 and 3 were drawdowns, flow tests. Buildups actually used to be the bread and butter of transient pressure analysis. I used to work Wyoming. I used to work in Oklahoma City, but I worked Wyoming. And Wyoming let us flare gas for 14 days on a new well until we got a pipeline connection. So what we did is we tested our well, we produced our oil to a stock tank, flared our gas, and then after 14 days, we shut in the well. Okay, we had nothing to do until our pipeline connections done, so we lowered a bottom of the hole and got a buildup at that point in time. That was common practice, not just for the company I work for, but basically, almost always you have to wait on a connection before you can sell your gas, and if you have gas production, it's nice to get a flow test. And in general, we were after 3 things on a buildup, a little bit different than a drawdown. We're after permeability, we're after skin, and who can tell me what else we're after?
Wallboard? Wallboard radius
Apparent wellbore radius is just a function of skin.
or? Okay.
E-star.
T-star. That tells us our reservoir pressure. Because if we're going to do like a numerical, build a simulator model to tell us what this reservoir is going to do, obviously permeability is always the most important reservoir characteristic there is. But initial pressure is very important too. Because in an oil reservoir, like the ones we were drilling in Wyoming, we want to know how far above saturation pressure we were to know how much production we'd get before we went into the phase envelope, and we have a big increase in GOR. And from a design standpoint, we want to know when we're going to have like larger separators, and was it going to be right away or a long time from now to handle a lot more gas. So these were important tests to run, but probably of all the well test analysis ever conducted or ever analyzed, most of them are pressure buildups, not drawdowns. As time goes on, there's more data, big data. So now a lot of wells have permanently installed, especially your offshore wells, have permanently installed bottom hole gauges. So anytime you're building up or drawing down or doing anything, you always have data that you can analyze.
Which is more accurate in terms of results.
What?
More accurate.
What about?
Like if you get permeability from the buildup and permeability from the drawdown for the same reservoir.
They should match. But they don't usually.
No, it takes time.
But there's always some justification. And in some cases, they're, your buildup's bigger than your drawdown because you're in a situation where your pressure's increasing and you're maybe fighting off compressibility effects, but also subsequent buildup, your building might be declining because of relative permeability issues. There's a lot of reasons why they don't match, but what your job is as an engineer is to explain that. Why aren't they the same?
I have analyzed a number of ways to get this results. And I got the DST data, I have 2 drawdowns, 2 builders. I analyzed the main drawdown, the main flow period in the DST and the main buildup. The results are never going to be matched. There is a huge difference. Like if I got a permeability of 10 Darcy in a buildup, I got a permeability of 6 or 7 Darcy in the
How long between the tests?
Like the flow is of 8 hours and the drawdown is for 16 hours.
No, how long between the 2 buildups?
What do you mean by that?
I'm sorry, maybe we're not on the same page. Should you run a build-up and a drawdown? I think you should run 2 build-ups and 2 drawdowns.
Like in the DSC, there's a main flow.
Okay, drill start test is an open hole completion. That's gonna be drastically different
But
mechanical.
you have some drawdown data from the DSC as well, and the main builder data. So you can analyze both the pace and you can get parameters like turbidity or pressure, and you can analyze the compare them. But they do not give you image. Even if it's open hole or the case hole, the results should be made because the calculations behind the equation behind the calculations are same.
I hadn't really thought about this before, or thought about bringing this into the course, but this radius of investigation, okay? Now, when I calculate a perm, I'm getting a bulk property to that radius of investigation. If I run a longer drawdown or a longer buildup, I'm looking at more reservoir. And I'm looking at different reservoir. If I'm looking at different reservoir, because I'm adding something onto the outer edges, I may, and it's thinning, or it's heterogeneous in that direction, I may get a different system. The only chance you have of actually getting the same results is to run 2 drawdowns after a long buildup between the 2 and run them the same length of time. I'm just talking about the idea of analyzing a different volume of rock. Drawdown versus buildup, you could have pressure dependent permeability. On your drawdown, you have overburden on your formation, and as you take pressure out of your pore space, your rock becomes more compact, and that could alter your permeability. Building it up would have the reverse effect.
But their compaction during the drawdown is so insignificant or so minimal, so you cannot take in consideration their compaction during the drawdown in your belt test analysis. Even if you take all the hydrocarbons from
I'm not saying this is easy. I'm saying that a lot of time is spent by reservoir engineers trying to explain the differences of the analysis over the life of the well. If you have a permanently installed gauge, you have almost an infinite amount of series of tests that you can analyze. Constant rate, constant pressure, variable rate, post equalization, the effects of different fluid regimes if you're producing from a 2-phase reservoir. So a whole science could be attributed to that. In general, we're trying to get ballpark estimates that we can make decisions on whether we're going to drill our next well or not. Now you can see I'm not splitting hairs with a lot of the stuff in here. 10% error in compressibility with the textbook and 4% with the viscosity or something like that. 57 and 63 millidarcies are the same number to me. Because the first thing we're going to do with any of those is either take the square root of it or the log of it to calculate in any kind of flow equation. And then that absolute difference becomes even less. But I certainly believe and understand your statement that drawdowns and buildups are going to yield different results. But again, try to explain why. And then you'll start to develop a reservoir engineering mind.
Excuse me. Is it more accurate to get the permeability from the build-up because we get rid of the Q varying the rate? Because in the flow test we try to measure also the...
There's always a Q, it's just the rate prior to the buildup.
Yeah. But I mean, that's almost one value, right?
Well, I think this headlines right here on the example 6.34, that this was a build-up post constant rate production.
Yes. It doesn't matter.
Yeah.
Yeah,
Yeah,
I know,
it's same queue
that's,
is drawdown.
but when you're doing the flow test, then you have your queue varying, and usually you
We
get.
have techniques to handle the situations called superposition when we
Yeah, I
have
know
variable.
that, but the problem is with the measuring tool that is measuring the rate. It's not always accurate.
It's mostly constant, that doesn't vary so long. The reservoir is not so dynamic. The subsurface conditions are not so changing. It should be the same most of the time.
I don't know how to comment on that. I mean, you do the best you can with rate. I mean, obviously, if you're filling up stock tanks, then it's up to the gauger to try to get a rate. It's not as good as this is natural gas engineering. Usually, you've got a pen or some kind of meter that gets a fairly accurate rate versus time on an instantaneous basis. So you can handle variable rates. But if you're not playing with the choke, it should be monotonically, slowly decreasing. And as we run into them, there's techniques to handle constant pressure production as well as the one we're looking at right now, constant rate production. It's not a perfect world. If you're stuck with everything being enough right to build up, you're actually in the wrong industry. You need to be a mechanical engineer, where ball bearings have to fit in sleeves, and you can have to have only certain tolerances. We don't know anything more than 2 significant ditches. And we usually only know permeability to the magnitude, okay? We gotta live with that. And we gotta go on with our work and make the best business decisions we can with that information. You got that? All right. I've done most of your work for you. Now, they tell us the initial pressure is 9,000 pounds, okay? But I'm telling you, we're going to determine that from the test. So let's put 10,000 pounds instead of 9,000 pounds. Just to make it math, okay? Because it's going to be an iterative process. Because I'm going to be using probably that initial pressure for my fluid properties, but then I'm going to get a P star and I may change that, okay? So let's just guess, and I don't want to guess too close. So I'm going to move it a whole 1,000 pounds away from what they told me, okay? To show that and typically we don't know initial pressure. That's the reason we're running a building. We do PWF. At time 0, our gauge is in the hole, and our flowing pressure at time 0 of the shut-in, at time 0 it's still flowing. That's an instantaneous point between when it was flowing and it was shut in. So we do know the flowing pressure. H is 21. They gave us a gas viscosity, a gas compressibility, and a Z. I like to box in and keep separate their numbers from my numbers. They gave us the gas gravity, 0.659. Global radius, 365. Our gas rate's really low, 100 MCF a day. Now that doesn't mean this is a terrible well. Maybe they felt like they could control the rate at 100 MCF a day better than easier than 1,000. If you're running a constant rate prior to a buildup, you want to run at a low rate because what if the well can't substantiate that rate? You've lost your opportunity to run a constant rate test. So the fact that the rate's low, seemingly almost non-commercial for a new well, usually you're talking about 1 million cubic feet a day, or 2 million, or 5 million, or 15 million cubic feet a day. 100 sounds real low. It doesn't affect the analysis, and the production engineer saying, yeah, I can maintain 100 MCF a day. That should be easy. You shouldn't have to do almost anything to the choke setting because it won't decline. If you started off at 5 million, you'd have to keep fighting it and keep opening the choke to keep it at 5 million cubic feet a day. So that's probably the reason we're looking at a test with a flow rate of 100 MCF a day. It does not mean it's a terrible well.
Or maybe the reservoir is tight.
Yes, it may be the reservoir's tight. Let's not rush to judgment. I tend to do. Okay, CT's up there. I'm not going to use their PAI. From here on out, I'm using pseudo pressure. Water saturation is 36%. I got that represented as the gas saturation is 64%. Okay, I'm done. Okay. Newly, okay, P-star Horner plot. Well, we learned about Horner plots. And then the other data that they gave us in here is porosity's 10, 210 for the reservoir pressure. They gave us this B sub G that we always put in our units. And they told us that there's Z. Okay. Let's just do a little work here. Well, let's. I don't think we need to do anything yet. Let's look at our time and pressure. Let's get let's get it from our textbook. What do we start at 120 or something? Oh, someone's going to ask me about wellbore storage. If you got a gas well or a oil well, even if you got a bottom hole pressure gauge, when you turn the well off at the surface, it's not turned off at the sand face. So the fluids continue to flow into the well until the back pressure is enough that the rate flows to zero. So in actuality, when you close in a well at the surface, you're not closing it in at the sand face. Another word for wellbore storage is afterflow. The formation is still produced. How does that pressure build up? The pressure builds up because you're flowing fluids into the wellbore, okay? Until it eventually kills itself. When there's no more pressure change at the thing, there's no more fluid flow. So a high perm well kills itself fairly rapidly and then starts to give us reservoir information. The tighter the well is, and also the bigger the wellbore. Now, when we were first testing tight gas, doing tests for tight gas and trying to get a pre-frac perm, and in this textbook, they'll use the wordage, downhole shut-in device. That means in order to eliminate or minimize wellbore storage, not only did they run a bomb to the bottom of the hole to get bottom hole pressure, they ran a temporary packer in the hole to shut in the well at the bottom of the well rather than at the top of the well, so that you only have maybe 20 feet to fill up before you kill the well. The well tended to kill itself. Is that enough about afterflow?
Yeah, just to solidify my understanding, these tests that we're doing are flow tests.
Yes.
They're not static tests. So what you're talking about is kind of the complementary effect of when you turn the well on for the test, you've got compressed gas that's at the same, it's at the average reservoir pressure, right?
Well,
and then it
this
takes.
way, in a drawdown, let's say you got a column of gas.
Yeah.
You turn on the well at the surface and your gas flows out immediately.
Right.
Is that the same rate that it's flowing in at the bottom? At time 0, at time 1? No, it takes a while. You're unloading. That's another term for afterflow.
Right.
During a drawdown, is you're unloading, and then finally those pressure transients get filled in the reservoir. Then you're producing in steady state.
Right.
Everything, the same rate, the same phase is at the surface. So you have wellbore storage effects on a drawdown and on a buildup. On a buildup, the terminology is after flow, and on a drawdown, the terminology is, what did you say? Unload. Okay. Pseudopressure and pseudotime. Okay, so we have a VB function for pseudopressure, and now you have a VB function for pseudotime.
Oh,
What?
oh, nothing.
You pretty excited about that?
Very excited.
Okay, so I should have put this in your package at the beginning of the semester, but I kind of debated it. And I've actually been working on it. And anyway, you now have this. So this is to account, again, pseudopressure and pseudotime were invented late in the transient pressure analysis chronology. Because we used to only worry about liquid flow. We used to only worry about oil wells. And by and large, the assumptions of constant and slight change in compressibility and viscosity were adequate, even for oil wells. But when we jump to gas wells, we're not in that league at all. Our viscosity changes and our Z-factor changes with pressure. So we have to account for that. And we account for that on the y-axis, where we plot pressure with pseudopressure, which integrates from some low base, all the effects of viscosity and all the effects of Z. Likewise, on the time axis, when pressure's changing, so we have this function of pressure that's a function of time, we have to account for viscosity and compressibility. And we did that with pseudotime. So from here on out, hit and miss, but by and large, we're going to use pseudotime for the rest of the examples. We can go back and look at the previous examples and add pseudotime in, but I look at them and they're not that important. So let's look at pseudotime now. So pseudotime is only going to be a function of time and pressure. And we have gas gravity, and you know what? We really need to discipline ourselves. Because I know that we're coming up with a problem that's going to have impurities. Okay, we got composition, we got reservoir temperature, and so we can calculate fluid properties at and we're gonna, again, I fictitiously made initial pressure 10,000 pounds to show that in general we don't know. I could make it 8,000 to make it 1,000 pounds less than what they said. We're actually gonna capture this when we capture pseudotime. So pseudotime is gonna change based on our estimate of time, of pressure. So let's see, I call it pseudo something, right? Pseudo, and pseudo TA is a nomenclature in the book, apparent, because we're going to multiply it. As much as I don't like pressure apparent, I love time apparent. And I have one for drawdown, which is that first one, and I have one for buildup. So I can see the pressure is building up, so I'm going to use my buildup. Okay, everybody got that dialog box? Okay. Time, I have to give it the array. Pressure, I'm going to give it the array. Okay? G is gas gravity. T is reservoir temperature. N2, CO2, H2S, and I have to give it an initial pressure. It's not required to calculate pseudo time to use initial pressure, but to calculate pseudo time apparent, I'm going to calculate pseudo time, and then I'm going to multiply it by viscosity and compressibility at initial conditions, and so I get an apparent viscosity and compressibility. It's not going to really change my analysis. Okay, and you can see in the dialog box down there at the bottom, I'm not just going to get one number, I'm going to get a bunch of numbers. I'm going to be able to fill in this array. How many of you already know how to fill in an array in Excel? You're going to learn something? Huh? Control Shift Enter. So I started my cell, I copy down, I hit F2, which is my edit function, and then I use 3 fingers and hit Control Shift Enter. Control Shift Enter.
Do you have a lot of different,
Now, Control Shift Enter may not be the same for Macs.
well, I was on, I did the define function of the same one that you did, but mine had different parameters in it.
Remember, there's 2. There's one for build-up, one for drawdown. Only the build-up prompts for initial pressure. You don't want to-
So what's all you have for your hours? Your, is it
10,000 pounds? 1,000 hours. Oh, 1680. Okay.
It is right?
What about it? You want me to do it again? Okay, let's just start over. I'm going to delete that whole thing. How about that? Does that help? Okay. Equals. Pseudo. Okay, there's 2 functions, pseudo TA and pseudo TA buildup. Double click, hit F in my dialog. I got to highlight all my times. And then all my pressures. Gravity, reservoir temperature, N2, CO2, H2S, and it wants initial pressure. The only thing it needs initial pressure for is to calculate viscosity, compressibility, initial conditions, and then it's going to multiply that to get an apparent pressure, just like we get apparent pressure from pseudo pressure. As much as I don't like apparent pressure, I do like apparent time. Okay, now I only got one number, 0, because this is 0. But then if I highlight where I want my array to go, and I hit F2, which means edit, and then Control Shift Enter.
It's giving me a compile here.
Makes you mad, doesn't it?
It's taking me to the DB. Automatically opens the DB program.
It's not too late to drop the course.
It's too late.
So what would we label these?
Unfortunately, you know, unless there's a lot of people having the same problem, you're just going to have to work with some of the other students to figure out what's different about what we did. Yeah, Gene?
I was just asking, what would you label these? 2 columns? Or the 1 column, I guess?
Should have time.
This is, I think that's the way the textbook would have it.
Okay.
They're delta T's, because we tend to have delta T's when we have buildups and T's when we have drawdowns.
Thank you.
But it's apparent. It means we've done the pseudoization testing. Sometimes my batteries are, I'm gonna check it. You know what? Testing. Oh, yeah, it's on. Where was I? What was I talking about?
The apparent.
Okay, yeah, the label. So I think that's what our text. Maybe it's TAP. Here it is right here, delta TA. That's what I'm getting right there.
Okay.
And you can see, the only reason I captured PI in my buildup is here's the real pseudo time. It's just the interval time, including the effects of viscosity and compressibility. Incidentally, I'm not really using CT, I'm using CG. But the SG is going to cancel from both terms. The leading coefficient and the SG in the denominator of the interval. They're constant, unless the gas saturation is changing. So that's my TA. So that's my time function. Now,
Excuse me.
yeah,
Since you just guessed the value of PI, would it affect over
only as a constant. It only affects that leading coefficient, okay? So no matter where my time is on my X scale, it's going to be a linear shift. So a slope that I get from this is not going to be affected. But now the intercept will. And that's what I'm after, the P star. So it'll be a slight iterative process to get P star. Okay, Horner time. T sub P plus delta T divided by delta T. What's my T sub P? 2,000. Let's move it up a little bit, it's so important. Equals T sub P. That's how many hours I produce the well at 100 MCF a day. Okay? That's my time produced. I've got to have for it. Plus, oh, you know what? I'll do this, but I shouldn't have started this on time 0, because I'm going to get a 0 divide. But I'm going to continue on so I don't have to waste any keystrokes. Plus delta T divided by delta T. So I'm going to get a 0 divide. I'm going to copy it down here. I'm going to get a real number. And there is my Horner time. Horner time allows us to, is a quick and dirty superposition function that is effective when we've only had one producing time. Now, our very first problem, we had different rates, different times, okay? This assumes we have, it's a superposition function, but it's a shortcut, quick and dirty. There's only 2 terms, T sub P and delta T. It's basically allowing us to look at our buildup data as if it was a drawdown. Okay, And then we plot that versus pseudo pressure. And do I have pseudo pressure? Yeah, that's good. I'm gonna get one at initial conditions. Equals M of P the pressure and interest. This will be the, I'm going to use this from time to time. This is my initial pressure right there. Everything else will be absolute. Okay, I'm ready to plot corner time versus pseudo pressure, so I'm going to insert a graph. Let me find it. Charts. Here we go. And it's a semi-long plot, so I'm going to take my x-axis and I am going to get a logarithmic scale. Let's play around here. Marker. Line, though. Nope. This is my markers.
Mirror format access, it says.
Oh, am I? Here's my marker. No fill. I want it red and I want it small. Here we go. Where's my size? Oh, that's just my font. Where's my size? Marker options. Here we go. Okay. Now, I've looked at a lot of buildups, and so I'm going to rush to judgment, and I'm thinking that along here is my middle time region. But we'll check that out later, okay? We'll run some quality checks, make sure that that's our area. Okay, but one of the things I can do is I can also put on a plot is the derivative. But we'll jump into that when we get into type curves, and we're also going to need Agrawal effective time. If we get to Agrawal effective time in a type curve, then we're in pretty good shape. I'm guessing that I want to use my tail end of my data up to a Horner time of about 100. So basically, this is what I'm going to run my regression analysis on. This portion of the data. We can come back and change some of this, okay? I'm just trying to run through how we can rapidly do an analysis. Okay, so my slope known Y's are pseudo pressures. And known X's are the log of my corner time. Okay? I'm probably missing a second thing. Okay, and then, like I said before, buildups and drawdowns, all your equations are going to assume that you have a positive slope. So this should take the absolute value of our slope. Okay. It's big because we have pseudo pressures. Okay, we don't really have to go any further to get skin now, right? I mean, to get perm. Let's go to 6.1 for buildups. Again, no one stop. We still haven't hit 6.1. Here we go. Not 6.10. I didn't know it was stop. So this is, for a buildup and a drawdown, it's exactly the same. Okay? The permeability calculation for a buildup and a drawdown is the same. So we can just come over to 6.3 and grab that. Our rate's 100 MCF a day. We've got to remember to open a paren and add 460 to our temperature, divided by our slope that we just got, and divided by h. Because we're really solving for kh, assuming we know our h. Oh, it was kind of tight. Is that what the textbook does for this?
103.
They got .029, is this the right problem? 6.4. .029 is what they got, and I think we're going to hold 272. Okay. It's not that hard to get an important parameter here. And I kind of rushed to judgment on, because I've looked at a lot of buildups. I'm familiar with this early curvature into a buildup, it becomes linear. I could be wrong. I thought the textbook was wrong in that very first example when there was like an earlier straight line and a later straight line after looking at the derivative. Let's look at our interpretation as far as a straight line going through our data.
Can you click on the slope real quick, just to see the series?
It's the data I highlighted. I picked up about 100 from the as the Horner time at the beginning. Let's put a data. Let's put a. We need 2 points. We need a slope and an intercept. Before we even calculate a scan, I want to put it my interpretation line on my okay. I need 2 points. Where's my graph? I want, for my slope and intercept, let's pick another point. Let's pick 10,000. Where am I going to do this? Let's do this right here. Okay. At 1. And, I'm sorry, let's put this down. At 1 and at 10,000. On my straight line should always be equal to the intercept plus the slope times the log of my x value. And I should have F4 while I was going along. And then that should give me another number for 10,000ths. It's a negative slope. But I took the absolute. If I wouldn't have used that absolute, this math would have been correct. I tried to get the math correct for my perm equation by taking the absolute value. So I had to add a negative sign. Let's put this equation on the line. Add. And this is a line that's going to give me my P star. X values are these two, and my Y values are these two. And it's going to think they're points, and I'm going to have to change them to line, solid line, not quite too pointy. And I want to get rid of the markers. Now, if I was just to make a subtle improvement, I would say that I use too much data. I use some of my, I went outside of my middle time region data. So I'm gonna use one less point. Remember, you can always make these adjustments. I do it all the time when I'm doing an analysis. Okay, now I've got an extrapolated P star, but it's in terms of pseudo pressure, which is why I wrote a function called pressure 1 that someone asked me about a long time ago. Who was it? Is it not in here? I see pressure. Is pressure 1 not in here? Gas PVT? I never gave you guys pressure 1, did I? You haven't? How'd you get it?
I don't know. Pressure.
Did you get it from a former student then?
No.
No, you gave it to us.
You gave it to us.
I got
How come
it.
I don't have it? I'll get it. grabbing too much stuff now, but I'm gonna get my gas PV team, just grab pressure 1. And then get rid of that module. Okay, equals pressure 1. I saw that the people in LSU had written that VB function that back calculates P from P over Z, and I found this was very useful too, because I want to actually calculate pressure from pseudo pressure. So my pseudo pressure is my intercept. That's my P star.
Excuse me. We're getting different pseudo pressures. I'm getting different pseudo pressures, so I'm getting different slope.
Yeah, I am too.
How much difference?
You're getting almost 190, I'm getting 180.
Yeah, I'm getting the same view on it.
There's no difference between 19 and 18. Let's move on. There might be some reasons. I've got a real mixed bag of software going on in the background right now. Okay, my pseudo pressure is my P star, temperature, gravity. Okay, I'm going to bold this number. This is what we are, one of the reasons besides permeability that we are actually looking for to get on a pressure buildup set. We want to know initial reservoir pressures, a very important characterization that we get.
The pseudo pressure you're using at what time is the pseudo pressure, the PP value?
The intercept.
Gotcha.
Okay, but I'm glad you asked. If you look at the fundamental equation, it's T sub P plus delta T over delta T. As delta T becomes infinite, what does corner time become?
The P star macro.
Pressure 1.
T sub P plus
Pressure
delta
Oh, yeah.
becomes 1.
Oh, 'cause it's one of her, it's itself.
Yeah,
It's big.
and the log of 1 is 0. And this is a semi-log plot, so it's the intercept. So, since we didn't run a really long, since our buildup was fairly large compared to our drawdown, we're almost to the y-axis. But it's hard to get all the way there. So we extrapolate, and that's how we get P star. And remember the textbook said it was 9,000 pounds. Yes.
How did you get to 10,000 slope or whatever, that number there? Over to your left?
I made it up.
Oh,
I could have made it 5,000, but it just showed.
no, the big number next to it. How did
Huh?
you? The number next to it. How did you do that one?
This is just y equals mx plus b.
Okay, I missed that.
You need to know y equals mx plus b to be in graduate school.
Yeah, I just didn't know how you calculated.
Now, and I cheated because I had to throw in a negative sign because I doctored up my slope. I doctored up my slope so that I could get perm using the textbook equation.
Okay.
Because the textbook always, and so then I noticed I got the wrong number here because that slope was actually negative.
Yeah.
And so then I had to throw in a negative sign. So I got y equals minus mx plus b.
Thank you.
So have a question for the slope used from maybe 24 and y intercepted given the E23.
Is what?
Like you will select the data thing. This one from E24, F24, something like that, right? The next one for intercept you use from actually 24. Oh, okay, sorry, no, mind.
Now, I actually, I changed my mind about that first data
Okay.
row. Unfortunately, I don't know a way to change my intercept and slope by changing one, but I can change them both. Okay, but I remember to do that because I've done this a lot. Okay, so I've got the two primary parameters that I'm after from a buildup. Initial reservoir pressure, and now we can play with this a little bit. And remember that I said my initial pressure is 10,000 pounds. And this gives me 8884. Now that I know that, let's type in 8884 up there. You see, I get a different result. See? 8868. Let's type in that number. 8868. And I get 8867. You see that I'm not changing it too much now. 8867, and I get 8867. To 4 significant digits, it took me 3 iterations to loop through there and find my initial pressure. Okay? That's why I thought it was blasphemy that they told me that the initial pressure was 9,000 pounds. This test is about trying to determine what the initial pressure is. But you got to make some educated guess. If I just got this data and didn't have this textbook number of 9,000 pounds, I would have probably taken the maximum recorded pressure $8,776 and maybe added 10% to it. Okay, as something to start with. Okay. I think that the other thing that we want to remember to do is recent files.
No.
Where's recent files? Okay. Recent workbooks. You haven't opened it yet. Let's apply. Where's, oh, it's already open. No, it isn't. This is my, I'm going to say this. I want to get my type curve. I'll get it over here. So this is the type curve we're going to put our data on. So we can just copy paste it into our spreadsheet. Okay? And in order to put our data on here, remember we have to do this every single time. Claims for comment. So we have to have a coefficient here and here. This is what you guys are going to do when you come, before you come to class next time. And then, let's see. You are going to have to basically come up X, Y, and Y prime. I didn't make enough. You have to come up with the coefficients to multiply X by and to multiply Y by, and Y prime. We also have to add a column for pseudo pressure prime. We can do that right now. I'm liking this technique right here where I skip. And see, this is this range where they become fairly constant. We're picking. So my x is just going to be multiplied by my t sub a, my y by my, I need one more column.
Can you hover over your PP?
Let me get this one little thing done, I will.
Okay, thank you.
My what?
The, I guess that's PP prime.
Derivative.
Yeah. Am I zooming in?
Natural logarithm.
Okay, thank you.
Delta pseudo pressure is my initial pseudo pressure that we worked hard to get. We had to take 3 iterations, except for it's my delta pseudo pressure, which I don't have anymore, do I? Oh, we were going to put it here. No, that's my PWF. Now I don't have my initial pseudo pressure anymore. Let's just put it right here for right now. I haven't done anything. Okay, I got 8867 iteratively. The pseudo pressure is that, and my delta pseudo pressure that I'm going to be plotting in my delta, in my piece of D column, is the change in okay, so delta pseudo pressures actually increase, don't they? I gotta have focus. Delta pseudo pressure, how come I'm decreasing? Oh, it's not. I made a mistake here. It's, I got this backwards. I knew I wanted this here. I knew I wanted the pseudo pressure for the pressure flow. What's wrong with that? Oh. I know why we got a bunch of mistakes. You see that I have that for the cell above it. Okay, let's fix this. That should be for the same row. I'm going to copy that up. So now I have my pressure flowing, copy that down. Delta pseudo pressure is always going to be equal to my current pseudo pressure minus my flowing pressure. And these increase. There we go. Now, That might be why we had some different numbers earlier. Okay? Let's look at I was, did you see that? I was a cell off. Now I'm going with that data. Now I'm going to play this iterative game one more time. 8917, 8917. Okay, took one iteration.
Because this will,
Did that help you guys with some of the other numbers when I fixed my error?
Can you go back up to the left?
Or on what cell?
Yeah, that's fine right now. I'm looking at the Horner.
Can you show the delta pseudo pressure?
It's the pseudopressure at time minus the pseudopressure of the well flowing. The pseudopressure of the well flowing is the pseudopressure of the pressure well flowing, which is at time 0. So that doesn't look very clear, but this one probably does look more clear.
Oh, yeah, that's much better.
It's not the cell above it, it's always absolutely at time 0.
Okay.
There's definitions of these things in our textbook. When we get into type curve matching, I've copied those labels right from the textbook. I already asked them. That's for linear flow. Green garden now. Okay, so that's my label heading, okay? And we have well more storage on this, so I didn't get you to get to the point we get to see. So if you want to solve for that, you can just take C sub D and multiply it by that denominator and divide by that numerator. Let's go up. Pseudo pressure versus time. Where is our P sub D next? Oh, right here. This should be easy. That's my column heading, P sub D over delta pseudo pressure match point. I get that number because I know perm. Okay, so it's KH divided by 1422 QT is the ratio of pseudo pressure and delta pseudo pressure. So once I know that ratio, I can multiply and get on my dimensionless type curve. That's kind of where we'll pick up. I don't think I got the right thing. Oh no, I did. Okay. So by algebraically manipulating this, you see that's my last term in parentheses. If I want to know that number, that I can ratio my delta pseudo pressure, I have that. I want P sub D. You have the wherewithal to at least get this column. We haven't done wellbore storage. I'm not going to go into it in the next 20 minutes, so we're going to stop there. But you have the wherewithal to calculate the J column. That's half the data you need to put yourself on a type curve. And then we'll put ourselves on this type curve. then we can see if we pick the right data. Okay, we'll stop there.